Hello everybody, welcome to this live webinar on the Picture Generation Unit Development. I'm Cédric Bélanger, Product Marketing Manager at OPTIS ANSYS, and today I have the chance to get the support of Thomas Lejeune, Sales Lead Generation. We deliver this webinar in live, so please don't miss the opportunity to interact with us using Bcast.
Exactly, Cédric, you can interact with us using Bcast. You have the link here, or you can just scan the QR code, and you will be able to interact with us, ask your question. So feel free to do it, and we will go through the question during the webinar.
So I'm pleased to welcome Sébastien Abraham,
Thank you. Hello everyone.
Head of Display. First, a few words about OPTIS ANSYS. So OPTIS is a world-leading company in virtual prototyping, recently affiliated with ANSYS. And ANSYS is a market leader offering the only true simulation platform with best-of-breed simulation across all major physics, structures, fluids, electromagnetics, semiconductor power, and mission-critical embedded software, and of course, optics. Regarding optics, we simulate the performances of light, human vision, and materials in interaction, ultimately allowing you to experience your head-up display system virtually before ever spending the time and money building multiple physical prototypes. So the topic today is the Picture Generation Unit. First, this webinar is part of a series. Mm-hmm. So I encourage you to, they are all free available on YouTube. So I encourage you to have a look, especially on the first of the series. Takes the lead on the HUD development in automotive. I did give an overview of our solution. Today, Picture Generation Unit Development. This is key because this is the origin of light.
Exactly. Yeah. Hello everyone. So yeah, the picture generation unit, as its name says, will generate the picture of the head-up display. So in fact, the driver will see the image that the PGU will create. So that's why it's a very important element of the head-up display. You need to meet several requirements in terms of mechanical constraint, in terms of thermal constraint, and in terms of optical constraints. So as you presented, Cédric, at ANSYS, we have a solution to manage all the part, like the thermal part. This webinar is more dedicated on the optical part, and we won't have the time to see all the use cases. We'll see two main use cases divided into sub-parts. The first one is the design and the analysis of a picture generation unit. And the second one is dedicated to the sunburn, the detection of the sunburn, and also we say a word about how to solve or to reduce the sunburn issue. So the first part is the design of a picture generation unit. So we'll design a TFT picture generation unit composed of several layers. The first one will be a layer to collimate the light. Then we have a layer to integrate the light, so in order to have uniform luminance at the output of the picture generation unit. And then we have layers to redirect the light on the fold mirror, and one layer for the TFT matrix. So we can directly go in CATIA. So here I have a system. So it's an augmented reality system. So here if we look on the housing box, we have quite big mirrors. And we will design the picture generation unit, so the element that is missing here. And for that, I will just, it's better if I hide the housing box. So to design this picture generation unit, we will start by the first layer, the collimation layer. And for that, on the picture generation unit part, I will create a new body, insert body, that I will call collimation. And inside this body, I will create a tear lens, a total internal reflection lens. So the goal will be to collimate the light. The light will come from this point. And here I will create a lens on this part. The origin, the support plane. And here I have several parameters, so I won't have the time to detail all the parameters, but in fact it's some simple parameters that describe the geometry. So the feature I will use is composed of it's complex geometry described in simple parameters that you can enter the correct values, or you can use the space optimizer to optimize the value according to a target. It can be a target based on the light. If you want a more uniform distribution of the light, or if you want to reduce some artifact, you can optimize this parameter to achieve this goal. So here I have one tier lens that will collimate these sources, and as I will have several sources on my picture generation unit, I will add on my collimation part a pattern to repeat this tier lens and have all the collimation layer with now the place for all the LEDs. So also an important point, I will affect up here. I will affect to this layer a material, as I will use later this layer on a space simulation. So I need to define the optical property, the space optical property of these materials. I can, if I measure this material, I can here enter the measurement of this material to have a precise description of the material. Here, as we as it's just a demo, we'll use a simple material with only one optical index. And we'll switch to the second layer, the integration layer. So the goal here will be to create this lens array. Just before I forget, I forget here to add a splitting part just to avoid this kind of here to avoid the geometry go outside of the PGU limit, like that. So then on the integrator, we'll create this lens array. So here we have one part of the integrator, and we'll do the other part on the other side. So for that, inside this body, I will add here an optic lens definition. As I collimated the sources is directional in this direction. The support, the support will be this plane, and I reduce the thickness. I will change also here the direction, the offset direction, as I want the geometry be computed on this part of the support. Then here I will describe the grid. So here you can see that there is a grid for the lens array, and on this tab I will describe the grid that I want. So the maximum, the size of the grid. And also the size of one element, so for one lens. I need also to position my grid. And now I won't change my target, and I will reduce the radius of my element. Okay. And now when I click OK, I generate the feature. And now I have my integrator layer. I will add, I will just hide this. And now I will show the other part of the integration layer here. So this will make the light be uniform at the output of the picture generation unit. And the next step will be here now to redirect the light to hit the foil mirror. So as you can see here, the light will be emitted in this direction, and we want the light to hit the foil mirror, so we'll redirect the light. For that, we'll use microstructure. And you can do that on ANSYS PEOS using the 3D texture here. So we'll define where we put the 3D texture, the support of this texture, and here we can take a cat part that I designed before this webinar, I just will precise how to position this part, and then I will show you the results. Up. Okay, and here on the preview, now I have the preview of the final result. So I can, of course, these elements are on all the supports here, and it will remove this part of the body to have a microstructure that will redirect the light on the correct direction. And the last element will be the LCD. So we have different way to modelize the LCD. Here we will modelize in a very simple way, just with a polarization plate and an absorptive part on the LCD body. But you can modelize, I will show you, You can modelize the polarizer, then the fact that the polarization of the light will turn inside the LCD using a half-wave plate or quarter-wave plate. You can also, if you have the birefringence material measured, you can enter your material here and describe very in-depth the behaviors of the light inside the LCD. Here for this demo, we'll just simulate the fact that the light is polarized, and we'll add an absorption coefficient inside the LCD. So here, here I have an absorption. So now I have all the elements of my picture generation unit. I will show you also that I have here the PGU box that will simulate the optomechanical part to avoid light go outside of my picture generation unit. And I will take all that into account in the simulation. Before I forget, I don't have the light here. So what I will do, I will go on the SPOS library and I will download a LED that I will use in my simulation. Up. Here. So now I can integrate the LED on my product, insert existing components. This one, open. And in this CAD product, it contains the geometry of the LED, but also the optical properties, so how the light will be emitted. I will show you here, center graph. So here I have the sources and how the LED will emit the light. So I can directly use this LED on my simulation. I will just correctly position the LED. For that, I will create an axis system on this point. And now, I will position by adding a constraint between this axis and the collimation axis here. So this one. And now my LED is at the correct position. So I need to repeat that for each position. So what I will do here, I will use a pattern to repeat, to position the LED on each position. So I will reuse the pattern I use on the collimation layer. So now, I have several LEDs that will highlight my picture generation unit. So before running the simulation, I will add two sensors. Up. No. I need also to display this. So here I will add a Radiance Sensor to measure the output of the picture generation unit, the luminance uniformity. here. I will reverse the direction. Geometric. Okay. And here, as I want my picture generation unit to emit light in this direction on the fold mirror, I will create an intensity sensor in this direction. So it's why I have this axis system, to be sure that the light is emitted on the correct direction. Up. I will use a conoscopic sensor, and I will just quickly edit the distance just for the display, as it's better that it's displayed here. So now I have all elements to run my simulation. So what I will do, I will create a direct simulation where my sources will be all the LEDs of my picture generation unit. My geometry will be the different elements of my picture generation unit, so my picture generation box, my integrators, microstructure, LCD, and collimation layer. And also, I need to not forget the 3D texture and the polarization plate we added. And for the sensor, I will use the two sensors I created here. I also need to edit the geometrical distance tolerance. So I edit the geometrical distance tolerance because inside my simulation I have a 3D texture that represents microstructure. So I need to have an accurate propagation of rays to correctly take that into account. So the simulation will take slightly more time, but it will be accurate.
Yeah, I think, Seb, it's time to remind the audience that starting from scratch, you have designed this PGU in 15 minutes.
Mm-hmm.
No trick here, no pre-record, no pre-calculation. And in 15 minutes, you are able to design
Exactly. So here we have a basis. Then we can optimize each parameter using the space optimizer to have a better luminance uniformity. Or to correctly, here we can optimize, for example, the microstructure I use to correctly hit my fold mirror. We can also add some elements like a diffuser at the end of the picture generation unit to cover more correctly my fold mirror. We can play with some parameters to collect the light we lose here, and so on. So it's allow fast iteration now, as you just have to run simulation, and you can use space optimizer to help you to do that. So I didn't also have time of doing that, but we can analyze so the TFT as I showed, but we can go very in-depth and visualize the propagation of the light in 3D inside the picture generation unit to correctly understand the different phenomena that happen. So it's bring to the analysis of the picture generation unit. So we see how to analyze a TFT PGU. Here it's the example also on a DMD PGU. So where the goal is to simulate and analyze a DMD picture generation unit. So we have the optical part, we also have the optomechanical part. And for the DMD matrix, we can download on this OPTIS library the DLP here, for example, from Texas Instruments. And if we do this simulation, we will, maybe it's better in full screen, we will simulate all what the picture generation unit produce. So we'll simulate what the final driver will see with some parasite light here due probably to the optomechanical part. So then we can use the light expert to understand exactly where this parasite light come from and solve these issues. Another important point is also to assess the luminance uniformity as output of the picture generation unit, as you want luminance uniformity, uniform image. You can do that in several ways. So you can download on the ANSYS OPTIS library the SAE standard that contains a luminance, non-uniformity, contrast, and contrast ratio metrics. Or if you have your own criteria, you can directly in ANSYS PEOS create your different targets and your different acceptance criteria, and you will have green and red lights that will allow you to check very easily if your design meet or not your optical acceptance criteria.
And so you are able to simulate the complete optical system. Does that mean you take all the optical effects?
Yes, we take all the optical effects that we need to take in the industrial part. So we take all the geometrical effects and more, because we take into account the polarization. We take into account different elements. The wavelength of the light is correctly taken into account. All the effects, in fact.
It's time for the sunburn detection.
Exactly. So the second part is on the sunburn detection. So as I say, we don't have the time to cover all the use cases. I choose this one because it's representative of one method. So here the challenge is to avoid, to prevent the damage caused by the sunlight on the picture generation unit. It's also you can also use that for the housing box. And then we will simulate the issue to correctly know, to measure the irradiance and to know if it will burn or not the picture generation unit. So the method behind that will have two steps. First, the detection of the critical sun position. So we'll do one simulation to detect all the potential critical sun position. And then from one of these critical sun position, we'll do a simulation of the issue to know if there is or not sunburn we must take care of. To simulate the sun, we will use also a standard to have for the spectrum of the sun that you can download from the ANSYS library also. And this method can be also applied to the housing. So to show you this method, I will go back in CATIA. I will just hide the PGU part and display, we can display the housing, and we can display the projector. So here, it's this plane represents my picture generation unit.
Yes, Seb, just remind the people that there are, you can ask all your questions on Bcast. So please connect to Bcast to ask your questions, because there are some people on YouTube, but they are not all. Everybody is not on Bcast. And
so exactly, if you have a question or if you want more detail about some part, you can ask your question. We'll answer the question at the end of the webinar.
Connect to Bcast to ask your questions.
So here the first step will be to detect the critical sun position. Sorry, the critical sun position. So for that, I will create a sources from my picture generation unit. So this sources doesn't represent the light emitted by the picture generation unit, it's just a method to detect the critical sun position. So these sources will emit the light in any direction. Here, here you can see that I have a illumination in all directions. Then I will create an intensity sensor here to collect the light in any directions. I will increase the size. And now what I will do, I will create one simulation that will take as sources the sources I created, same for the sensor. And on the geometry, I will take into account all the geometry of my system. So here the cover lens, the windshield, the mirrors, but also the housing part. I will activate the light expert, as I will use this light expert just after. And now we can run the simulation. Yep. So this way I will detect all the potential critical sun position. So now if I open the results, up here, I have a map with the different critical sun positions that we can see also in 3D. And up, and here we can see the different area of this map, where the sun comes from for the different area. So for example, this one comes from a direct illumination of the sun into my picture generation unit. So it's because I lack of some geometry, so this issue can be solved by adding here the geometry. Then we have this area that comes from the classical path, so the light that directly go on the correct path of the light, I would say, so the path designed for the picture generation unit. So in this case, you can't add any geometry, so we'll see just after how to solve that, but it's mainly with cold mirror. And if we look closely to the result, we have here, for example, another part that will give us the different light path. So here with a double reflection on mirrors, for example. So this way, you can understand, analyze each potential direction for the issue, and then correct it. So now from that, you can extract the sun direction. Here I extracted one that hit on this issue part. And I will create a sensor, a new source. Here, in fact, I will position a sun in this direction to analyze what's happening when there is a sun here. So sun in this direction. And for the spectrum of the sun, I will go on the library. So here I already downloaded the spectrum, but I can download from the library. And I will create now a simulation. Now I need a sensor on my picture generation unit to measure the irradiance, the incoming irradiance from the sun. Projector, file layer. So here, I will create this sensor at the size of the picture generation unit. Okay. And in radiometric unit. And now I can create a new simulation that as sources will take the sun, as geometry will take all the geometry of my previous simulation, and as sensor it will take the radiance sensor I created. So I run the simulation. So on a real context, I will increase also the number of rays to have more accurate results. Here, for demo purpose, it will be enough. And here I have the issue, in fact, what this sun direction will create on my picture generation unit, because some light is focalized with the freeform shape of the mirror. And I can measure here the maximum luminance. The maximum irradiance. Here, 30 kilowatt per meter square. So here I have an issue. For example, it will burn my picture generation unit. So I need to take care of this light path. So here, as it's an augmented reality system, I have a big zoom factor. So sunburn is really critical on this kind of system.
So we are able to detect, quantify the sunburn on the PGU. And we are able to assess and compare the different solutions in order
exactly,
to resync.
So just to reminder, we can do the same step, detect the critical sun position and then detect the critical area on the housing. And we can also present results in a more easy way to understand. So here we include in the sensor a template to distinguish 3 different zones: the non-critical zone in green, the temporary glare in orange, and the permanent damage in red. And we can do that for several sun directions. We have Optim1 that allow to run simulation on several parameters. Here, the sun direction. And what you say to compare the solution, so different kind of solution, I would say, exist. It's basically the same principle. The principle is for cold mirror to reflect only the visible part of the light, And for cover lens, it's the exact inverse. It will let only the visible part go through, or avoid the non-visible light to go through. The goal is to avoid the maximum of light inside the housing. And we can do the simulation as SPEOs take into account all the aspects of the light. It of course take into account the coatings. And we can do the simulation to compare the solution to see for several sun direction we still have issues, for example. So then we can redesign the system, change some the place of the mirrors, the layout we designed for the system to avoid this kind of issues. Okay.
Okay, thank you. So I think we are almost on time for the question and answers. So Thomas, do we have any questions? First, maybe you want to make comments on the
so the CloudWorks was working very well. I think it was displayed on the live. But now it's time for 2 questions. The first one is what would be the benefits of using this solution? And the second one is what is the gain regarding to your actual process? So you can answer to this question right now on Bcast. And we don't have any question yet. I think you were very clear. So maybe we can wait.
Of course, if you have questions even after this webinar, you can contact us on the Optis website, Optis World website. You have a contact part and you will find the closest subsidiary to ask your question. Don't hesitate to do that, because here we present only a small part of what we can do with our solutions, as we are limited in time. But we can cover all the aspects of the light and all the issues linked to the light.
We also are on LinkedIn, so there is a SPEOs user group, so you can also reach us through LinkedIn. And we have another webinar to come, end of November.
Exactly.
On Stralight.
On the Stralight analysis. So it's also an issue due to the sun, like sunburn, but it affects more the visibility for the driver. It blinds the driver. So we'll see how to detect that, how to analyze it, and so on.
So I will send you the invitation for the next one, for the next webinar, end of November. Well, the Bcast is still open, so you can
feel free to finish the question, and if you have one you can write, we can answer after the live.
Maybe you can display the result of the cloud world.
Yeah, sure. So the cloud world is just here.
So
simulation there, optics.
The challenge during the development.
Okay.
Optimization. I think we have we address the simulation. We address the library.
Yeah. We address all words here.
Optimization.
Indeed, in the optimization part, we address that also. I didn't details how to use it, but we have a SPEOs optimizer, so we can optimize one parameter. So here it could be a parameter of that I use to design the picture generation unit based on a target that is an optical target. So it can be the luminance uniformity at the end, or if you want to target a specific power, I would say output power of the light, you can also. So you can link a target with a parameter and optimize that, or several targets with several parameters.
Okay.
So it's also something that we can cover. We don't have the time to show that, but
yeah, but I think we covered a lot of it was very interesting, and I think we demonstrate that we are able in 30 minutes to have a PGU, to design a PGU and to optimize it to detect the sunburn.
I think early in the process it's very useful to have a quick
in 30 minutes.
Yeah, so a quick proof of concept.
So that's the message of this webinar. Thank you very much.
Thank you.
Thank
you guys, and talk to you very soon. Bye bye. Stay tuned.